Hello, everyone, and welcome back to your channel of probability and statistics. We started last time to talk about continuous random variables, and we saw the difference between those and the discrete random variables. Like we did with the discrete, we are going to look at some of the most important like models in the continuous variables. And the first one we are going to start with is the easiest one, well, or the second easiest after the uniform, of course, which is the exponential distribution. You must have heard me saying that in the discrete word, for discrete random variables, the gamma function, or I'm sorry, the geometric random variable is uh, is possessing a property called the memoryless property. Like, remember, I give you a very simple example of tossing a coin. If you get four heads in a row, what's the likelihood that you get a head in the next time or a tail in the next time? It's still one half. So it's as if the process itself forgot forgot everything that happened before that instant. Well, the exponential distribution is the same thing for continuous random variables, and we can prove that, or we will prove it, okay? So the exponential distribution also something else in the discrete random variables. We said that if I have a rate of arrival, we usually use the Poisson distribution if that rate was the rate was basically proportional to the length of time. So if I say I get common sense, four customers per every 15 minutes, then on average I get 16 every hour, right? It turns out that if a process has Poisson arrivals, meaning the arrivals follow the Poisson distribution, then the time between arrivals would be exponentially distributed. So the exponential distribution has a relationship to the geometric on one side for forgetfulness. What did I say before? No, I'm not exponential. And has another relationship with the Poisson distribution is if the arrivals follow a Poisson distribution, then the inter-arrival times would be exponentially distributed. The function for the exponential distribution is one that you should be very familiar with in the case of, when if you did math so far, and it's lambda e to the negative lambda t or x. Well, let's say that f of t, because usually it's for time. Okay? Lambda is greater than 0, and t is greater than or equal to 0. Okay. So basically, this function looks something like that. The probability density function, f of t. This is x. And this is t. Notice t is greater than 0, so we cannot start to the left. So this is f of x, if we say x, not t. And it's going to look something like that, where this is lambda. And the mean here, mu sub t equals 1 over lambda. Okay? So the mean would be 1 over lambda. And the standard deviation is also 1 over lambda, meaning the variance is 1 over lambda square, meaning the mean and the standard deviation are equal. That's how much variability is in the exponential distribution. Remember, I told you there was a relationship between the exponential and the Poisson, but in the Poisson, the mean was equal to the variance. So the standard deviation was the square root of lambda or mu. We call it there mu, the square root of mu. But here, No, it's equals to the mean. We will take some examples, but you will see about that. Um, of course, the cumulative distribution. So if I say um, f of t equals the integral from 0 to t of lambda e to the negative lambda x dx, or lambda y dy, it doesn't matter. Notice that lambda is a constant. The integral of e to the negative lambda t is 1 over negative lambda e to the negative lambda x. X, I mean, not t. So when you integrate, when you simplify that, or when you evaluate it, you will get equals negative e to the negative lambda t minus e to the 0. And since e to the 0 is 1, that becomes 1 minus e to the negative lambda t. So the cumulative is 1 minus e to the negative lambda t. Right? 1 minus that. Um, okay. After that, we can find probabilities of anything. So it's like, maybe you can find the mean first. So if you want to find the mean, e of x or e of t equals the integral from 0 to infinity. Notice the moment the function goes from to infinity, but it's not negative. So time of t e to the negative t lambda. So lambda is constant, we can take it out. E to the negative lambda t dt. Okay, so the lambda is constant. Now you have uh, a product. So you can use integration by parts if you wish. Remember, I showed you, well, that was in the math uh, channel, that we usually say dni, the derivative. You see that t, when you keep taking its derivative, it will disappear. E to the negative lambda t is easy to integrate. So you get 1, then 0, and this is negative e negative 1 over lambda e to the negative lambda t, and then you get 1 over lambda square e to the negative lambda t. Then you say it's this plus and this minus. Notice we have the lambda out, so we didn't, and the integral of that is negative 1 over lambda t e to the negative lambda t minus 1 over lambda square e to the negative lambda t, and these are evaluated from 0 to lambda. So when I evaluate at infinity, I get e to the negative infinity is 0, right? And you would say, what about the t? Yeah, if you say t over e to the lambda t and use L'Hopital, you will get 0 anyway. So this is 0, and here e to the negative lambda t if is also 0, right? And then when you do the 0, t is 0, so anything times 0 is 0. And then here, when you get 0, e to the 0 is 1, so you get negative 1 over lambda square. And when you multiply all of that, you have 0, negative times negative is positive, so you have lambda over lambda square, or 1 over lambda, like we said. And if you do the variance, you will get 1 over lambda square, and then you take the square root of that. It will give you that the standard deviation is the same as the mean. Something else you can do. Where is the median? Is it to the right or to the left of 1 over lambda? Common sense would say is to the left. Why is it to the left? No, not because it's raining, usually when you say to the left. Anyway, uh, okay, if it's one to the, I'm sorry, if it's, we know that if you have a distribution that is symmetric, like the uniform distribution, then the mean, the mode, and the median, all of them are the same value. But if you get a distribution with um, a distribution, we didn't talk about skewness yet, but positively skewed, meaning it has a longer right tail. What does the longer right tail mean? It means that we have a few outliers here that have very large value, right? And we said that the outliers affect the mean more than it affects the median, meaning they are shifting the mean to their side more than the median. So the median stays pretty much the same in the same location, but the mean is stretched. So I would expect the median mu tilde to be somewhere here. And how would you find that? Remember that we found the cumulative distribution function. Cumulative meaning I'm going from 0 to infinity, keep adding the area. And I know that the area is 1. And I know the area where the median is located from 0 to the median is 0.5, right? The median is when it's dividing the data into two equal parts, starting from the smaller going to the upper. Or you can start from infinity and come back. It's the same thing. But now if I say the cumulative at, let's call it t tilde, the median, equals, well, it equals 1 minus e to the negative lambda t tilde, and that equals 0.5. It has to equal 0.5. So when I move this to the other side and move the 0.5 here, I get e to the negative lambda t median equals 0.5, right? Or I can say um, e to the lambda median equals 2. You can do that, but you can easier take the natural log. So you say negative lambda t tilde equals natural log of 0.5. Like we said, we can write this as lambda t tilde equals natural log of 2. So t tilde equals natural log of 2 over lambda, not 1 over lambda, but the natural log of 2 is less than 1 because E is 2.71. So the natural log of 2.71 something over lambda is 1 over lambda. So this must be smaller. And of course, if you take the natural log of 2, you get 0.693 something, 0.693, roughly 70% of the mean. So the mean is larger than the median. And it happens every time you have a longer right tail in a distribution. And the opposite, of course, it's a left or negatively skewed, meaning it has a longer left tail. You would see that the mean would be to the left of the median. And the mode usually, and the median is always or usually between the mean and the mode. So the median is in the middle for unimodal, because we have distribution that has two modes, bimodal. We are not talking about these now. The last thing I want to show you in the exponential distribution, and maybe we'll stop here and then next time we'll start working with the normal distribution, which is like, will take a long time working with these. So memoryless property of the exponential distribution. Okay. Remember when we did the conditional probability earlier in the course, right? Now I want to say, so the idea is if I have an object following an exponential distribution, like its life, a life of an element like a light bulb or many electronic uh, devices or many electronic uh, parts usually follow the exponential distribution. And we say, well, given that my part has survived 100 hours or 1,000 hours so far, what's the likelihood that it will survive an extra 100 hours? Well, it's the same as a new part, the probability that a new part will survive 100 hours. Why? Why? How? So, for example, if I say find the probability that t exceeds 1100 hours given that t is greater than 1000 hours. Okay, right? Doesn't that make sense? The condition is that it already survived 1,000 hours. What's the probability that it will survive an extra 100? I remember, or do I remember? Did we remember how to find the conditional probability? Remember we divided something by something. We called the top. You remind me. I'm feeling exponential today. I don't have, I'm the memoryless property. Okay. Okay. It says the probability that t exceeds 1100 and t exceeds 1000. Remember what we call that? The joint probability divided by the probability of the condition that is called the, huh, you find it in the margin? Yes, marginal probability. What do you have at the top? If I tell you I have I have some kind of device. It survived 1100 hours and it survived 1000 hours. You say, of course, if it survived 1100, then it definitely has survived 1000. What, are you crazy? You mean I can write it easier? Yeah, very simple. You say it's the probability that t is greater than 1100. So everybody would know it survived 800 and 900 and 1000. Are you out of your mind? Divided by the probability that t exceeds 1000. Oh, this, by the way, the probability that something exceeds something is the opposite of the cumulative because the cumulative distribution is the probability that t is less than or t is less than t, right? Going from 0 up to that point. So the probability that t is less than t is called the cumulative. So the probability that t is greater than t is 1 minus the cumulative. But the cumulative is that. So if I say 1 minus negative e to the negative lambda t equals e to the negative 1100, right? 1 minus negative. So it's positive e to the negative 1000 lambda or 1000, yeah, 1000 lambda. So this would be e to the negative 1100 lambda, and this would be e to the negative 1000 lambda. You learned from math that if we divide two exponents, you subtract them, so you get e to the negative 1100 lambda minus 1000 lambda equals e to the negative 100 lambda, which is the probability that a new part would survive 100 hours. By the way, we call that function e to the negative something without, so the complement of that. Notice if this is t and that is the cumulative 1 minus e to the negative lambda t, so that must be e to the negative lambda t. So when I add them up, these two cancel and I get a probability of 1. So that's why we call that the survival function. Or another word is the reliability function. So the reliability of an element is always measured at a specific time. So what is the reliability of that object after 100 hours or 200 hours or 1 million hours? Okay, depending on the parameters that govern that. So basically, again, if you want to find the probability between any 2 points, it's the same cumulative, and you evaluate instead of evaluating it from 0 to t, you would evaluate it, say, from 100 to 200, whatever. Um, and the funny part about the that distribution is that, um, as I said, the integral from 100 to 200 is the same as the integral from 1000 to 1100, or between 500 to 600. It's the same if the period is constant. From 1000 to 1100 is the same as from 0 to 100. Okay? So that's why the exponential distribution is the easiest distribution you encounter, and it's, as my academic advisor used to say, it's the mostly used and abused probability in the reliability, because it's very easy to deal with. Okay, so we will stop here, and next time we will start with the most important. Uh, keep watching and have your seat belts. We are going to ride with the normal distribution. Thanks for your time. Have a great day.